Welcome to qnawire.
Our question wants us to consider an electromagnetic coil with a diameter that is made from square wire. The square wire has a length of 2 millimeters. So L here is 0.02 meters. And the diameter of the coil is 2 meters. So D here is 2.0 meters. Okay. We're also told that the power supply has a voltage V of 35 volts and a maximum power output of 1.0 kilowatts, which I call P of 1.0 times 10 to the third watts. We know the copper wire here, or the wire here is a copper wire. So I also write the resistivity of the copper as rho, 1.68 times 10 to the minus 8 ohms per meter. For part A, we're asked how many turns are needed to run the power supply at maximum power. Well, the first thing we're to consider is the equation for power. So power here, and let's indicate this as part A first. Power here is equal to the voltage squared, V, divided by the resistance, R, where R, the resistance, is equal to the resistivity, rho, times the total length here, not just the length L, which was the length of the square copper wire. We're talking about the total length L, which is the length of the wire when the voltage power is maximum here, divided by the area A. Therefore, we can express the length of the wire, given these two equations, from the voltage at maximum power as L is equal to, we'll use capital L here to distinguish it from little l. L is equal to the voltage squared times the area divided by the power, P, times the resistivity, rho. Here, let's make sure we have enough room, actually. There we go. Power P times the resistivity, rho. Well, N, the number of turns here, is equal to L, the total length, divided by 2 times pi times the radius, but the radius is d over 2, right? Since we were given the diameter. So we just have the expression for L on the left side there, so we can replace that and simplify a little bit. So this is V squared times the area divided by pi, because we can cancel that 2 with the 1/2, pi times d, actually, not times r. There we go. And the area here, since it's a rectangle or a square, is just the square of little l. So this is little l squared divided by pi times d. Oops. So I ran out of room on this page, but if you go ahead and plug that in and run that calculation, we find that N here is equal to about 46 turns. So remember, you have to round up because you need the maximum number of turns, right? All right, so that's our solution for A. Part B says that it wants us to find the magnetic field strength at the center of the coil. So to calculate the magnetic field strength at the center of the coil, we simply use the equation that says the magnetic field B here is equal to magnetic permeability of free space, mu naught, times the number of turns, times the current, I, divided by 2 times R. Again, where R is D over 2. Or excuse me, 2 times R, the resistivity. Okay. So now we just need an expression for the current, but the current here is equal to P over V because the power is equal to the voltage over the current. So we have mu naught, which is 4 pi times 10 to the minus 7, times N times P divided by 2 times the voltage times R. Plugging those values in, we find that this is equal to 0.83 times 10 to the minus 3 Tesla. You could also write it as 0.83 millitesla, but I'm just going to leave it like that and box that in as our solution for part B. Lastly, part C is a conceptual question that says, if you use a greater number of turns in this same power supply, will the magnetic field result? Increase or decrease? According to B, the number of turns in increases the magnetic field. But we also have to consider the fact that if increases, so we can say that if in increases, the resistance R also increases. And if R increases, we can say thus, if R increases, I, the current, will decrease because they are inversely proportional. So if N increases, R increases, thus I increases, even though B also is linearly proportional to N, it will not result in a net increase. So it will actually stay the same. So we can say, we'll type this out. Therefore, the B field is unchanged. We can go ahead and box that, all of that in as our solution for part C, which is the final part of the question.